What I'm going to do with you students right now is go over an old quiz I gave in winter 2012. This is quiz 15. It's a spectroscopy quiz, and I just want to go over it to make sure that as you are studying, you know what to look for and how to look for it. So in this particular quiz, I had given them the molecular formula of the compound, which is C6H12. I gave the IR spectra, the proton NMR, the carbon NMR, and a blow-up of those spectra. So I hope that you've taken some time to work on this on your own. When you've done so, you want to come back to the recording. If you haven't, pause it here and then turn it back on after you've had a moment to try this on your own. Okay, hopefully you've had a moment to look at this. This is the key to that particular quiz, and I'm going to go over it with you in such a way that hopefully you understand what it is you're looking for. First things first, I would always take a good look at this molecular formula, which in this case is C6H12. If you know that formula, you should be able to compare it to what the molecular formula should be for a totally saturated system. With 6 carbons, the total number of hydrogens you would have in a totally saturated system would be 14. And 14 minus 12 is 2. And 2 divided by 2 is 1. So you have 1 degree of hydrogen deficiency, which means that you either have a ring or a pi bond somewhere in the ring, or sorry, a pi bond somewhere in the system, which means that you have an alkene. Now, the IR should let you know which one of those two possibilities it is, and you'd want to be looking for the presence of a double bond or lack of a double bond to figure out which of those two it is. Now, I have circled the important peaks here in the IR that you should be able to identify. If you find 3000 here, you do have a peak here to the left of 3000. This peak here that's almost at 3100 wave numbers is for the sp2 carbon hydrogens, which suggests that you have a pi bond in this molecule. So you're not dealing with a ring, you're dealing with an alkene. And to verify that it really is an alkene, I would also note that there is a carbon-carbon double bond at 1650 wave numbers. It's not at 1700 wave numbers, it's at 1650. So this is the carbon-carbon double bond. Also, just below 3000 wave numbers, you have a whole bunch of peaks here for the sp3 carbon hydrogens. So what I'm learning from the IR is that I definitely have alkane and I definitely have alkene. So as I look at the proton NMR, I would want to be thinking about where would I find alkane and alkene type signals. So I have come back here for a second to the PowerPoint slides that I gave you. This is the chemical shifts chart. So for alkanes, it lets you know that if you're dealing with carbon hydrogens on an sp3 hybridized carbon, those signals should show up somewhere between 0.9 and 1.8. That is the typical region for finding alkanes. And the typical region for protons coming off of alkenes is from 4.5 to 6.5. So these would be for the protons directly coming off of a double bond. Okay. One other thing that I would kind of like to know is if I have any protons coming off of a carbon adjacent to that double bond. So I know I'm going to have a double bond, but if I have a proton on an sp3 hybridized carbon adjacent to that double bond, it should be between 2.6 and 1.5. That's a normal region. And just to point it out, if you have a proton on an sp3 hybridized carbon adjacent to a pi system, it doesn't have to be a double bond, they tend to appear in similar regions, whether they be benzylic, allylic, or next to a carbonyl group or a nitrile group. They all tend to be kind of in that same region, just so you're aware. So now we're going to go to the key and take a look at that proton NMR. Now, I'm not going to show you the answer right now. This is the larger full spectrum, so you can see what actually is here. Looking at the locations of the signals, I would hope you would see 1, 2, 3, 4, 5 different signals. So 5 different types of protons exist in the molecule. And again, that region for the protons on the sp2 hybridized carbon are between 6.5 to 4.5. So this signal right here is in that 6.5 to 4.5 region. These would be protons coming off of the alkene. And the region between 0.9 to 0.8 would be the alkane region. And again, remember, if you're on the sp3 hybridized carbon adjacent to the double bond, so you're of allylic position, you should be around 2.5 to about 1.7, 1.5-ish. So right in this area here. And this signal right here at 2, I guarantee, would be adjacent to that double bond. This one is questionable. It might be adjacent to the double bond. It might just be a normal alkane next to other alkane signals. It's kind of in an iffy area. But this one should be adjacent to the double bond for sure. Something else I'm noting here would be the integrations. This would be the line that I am tracing for you right now. Okay. And again, these are ratios, so you got to remember you're looking for ratios. The smallest of those peaks to me appears to be this one right here at 2. It appears to be a little bit longer than 1 unit in height. So I'd give it a ratio of 1, and you can see initially I had put a 1 there. I scribbled over it and put a 2, but initially I really thought that was a 1 because we're talking about ratios. And this peak here appeared to be about the same height to me. It was a little over 1 unit in height for this integration, so I said it was also a 1. And then this signal here at about 4.6-ish, I also thought looked like a little bit more than 1 unit, so I said it was the same ratio of 1. And then the signal here at about 1.7 and the one at 0.9 I thought were a little bigger than that. It's not quite 2 units in height, but it's definitely more than 1, so it's probably about 1.5, and I know I can't have a half of a proton, so I said it was 3. And if that's 3, I bumped the others up to 2 so that I could be dealing in whole numbers of protons. And that one appeared to be about the same height as this one. So when I got through doing the numbers, I had 2, 2, 3, 2, 3, which if you add it all up equals 12, which is the number of protons that we are dealing with. Also, the carbon NMR. I'm going to quickly scroll through that so you can't see the answer quite yet. These are the important parts of the carbon NMR. And there are 1, 2, 3, 4 peaks in the sp3 region. And there is 1, 2 in the sp2 region. And again, that sp2 region runs from 110 to 160 parts per million. Something I would note about these signals in the carbon NMR is you have 6 carbons in this molecule, and you have 6 signals, so they're all chemically unique. You don't have anything that is chemically equivalent based on that information, and 2 of them are from the alkene. That's a good sign because we saw that in the IR. We're also seeing signals in the proton NMR for an alkene, and we're also seeing something that appears to be alkene-like. As I look at these alkene signals, though, one thing I would note is that this one is short. This one right here, just beyond 140. And that probably tells you that there aren't any protons on that carbon. If you remember in class we said if they're short peaks, they probably don't have protons on it. And that one's significantly shorter than this one here at 110. So one of them has protons and one of them doesn't. Now, I'm being careful so I don't show you